Okay, so in this video, we'll talk about Aspen Plus Tutorial 1. Tutorial 1 should have been posted on Blackboard. It's basically this guy right here, right? So just have a look at it. It's not that long. It's just an introduction to Aspen Plus. It talks about Aspen Plus version 9. However, the changes should not have been that big between version 9 and version 11. And this is a two-screen type of scenario, or maybe you need to print it out, or maybe you'll read it on your phone, or maybe just jump between windows. But um, give yourself some time to really try and absorb Aspen. It's an extremely important skill. Okay, so let me move on to Aspen right here. Let me see. Okay. Here it is. Okay, so this is Aspen Plus, and as you can see, once you start here, you get your basic landing page where you either open or generate a new file. For our purposes, we're going to generate a new file, right? Starting something new. And we're going to generate a blank simulation. If you look on the right-hand side, Aspen has a lot of base cases. You can look at scenarios, look at many things. For our case, we're going to look at a base case, right? Okay, let it run. Might take some time, depends. So I have Aspen installed on my machine because I use it for research and things like that, or writing manuscripts. So if you're accessing it remotely, as we said in the previous video, it will take time to. So just be patient. Give it some time. Just be patient with these computers. Okay. Okay, here we go. So this is the general layout of Aspen, right? The most important thing you need to look for basically is on your left-hand side here. Bottom left-hand side, I have four things: Properties tab, Simulation tab, Safety analysis, Energy analysis, right? The safety analysis and the energy analysis are more of advanced features, or let's say optional features not used that much in Aspen. There are other packages which will do your safety analysis or maybe do your energy analysis for you. But so for this semester, we'll only be looking at the properties and the simulation, right? Let me get rid of this guy. So you always start with your properties, and the objective or the purpose of your properties tab is you need to specify the chemicals you're going to use when designing your process. And this is very similar to what we talked about in the slides, where first step is creating a database of chemicals. I need to know what chemicals I'm using. And once I know what chemicals I'm using, I need to specify the thermodynamic method which best fits these chemicals, right? And Aspen Plus does have a thermodynamic, thermophysical, physical database, whatever you want to call it. So all you have to do is call up the chemicals here, and Aspen will do the rest. Once I'm done with this, I'm going to go to the simulation to drop my basic units, start building my flow sheet, my base case, putting in some flow rates and some temperatures and pressures to start running. So in tutorial 1, we're looking at a simple case where basically, let me switch my screen back to tutorial 1 here. So tutorial 1, as you can see here, we're doing separating N-hexane and N-decane, two hydrocarbons, using distillation at high pressure. So I have 100 moles per minute of N-hexane, 100 moles per minute of N-decane, 70 degrees Celsius, 1 bar. I put them through a pump to pump them to 5.2 bars, put them in a distillation column, where I'm basically separating hexane at the top, which is the light end, and decane at the bottom, which is the heavy end. And then I put some distillation column properties, such as your reflux ratio, your boil-up ratio, number of trays. You're going to cover all of this, I think, with Dr. Ilyas in your mass transfer and separation course. But for now, just let's go through this tutorial and just try and replicate this process, right? Let me jump back to Aspen Plus here with the screen share. Okay. So my first component, I have two components, right? N-decane and N-hexane. So let's write them here. So there are two ways to find a component. If it's a common chemical, you can just basically write the chemical name. So as you can see here, I'm writing the chemical name. Right, and then Aspen automatically recognizes it. Alternatively, you can click on this find button, and I'm gonna write decane and search, and it's gonna search in its database for all types of all the chemicals which have this string decane in it, right? And then you can select it from a list. So if it's a very basic chemical, you might save yourself some time by just writing it, and you either press tab or press enter or whatever for Aspen to recognize it. If you're using a complex chemical, you're not sure about the spelling, you have the structure, you don't have the name, you can use the search database. And if I write decane, you can see all types of things happening here, right? So we're looking for N-decane, right? So let's see, let's try and find it. N-decane, here we go. And you just double click it and it shows up, and you close out of this window. And you just have to be careful because the Aspen interface, previous students found it to be sticky, where once I select it, where do I go with this chemical? Where do I go with my mouse button? Whatever it is, just keep an eye on it. Just get comfortable with it, practice it. You're gonna get used to it extremely quickly. Okay. So we're gonna, in your tutorial, you're being asked to Okay, so in your tutorial, we have part 1 where they tell you to open a blank simulation. And then actually in your tutorial, they ask you to go to your setup page here under specifications and define your units. And again, at this part, you can define, this is the stage where you define your units. If you want to use, pounds, Fahrenheit, Rankine, or if you want to Celsius, or use metric units, SI units, English units, you specify it at this stage, right? So for tutorial 1, they're telling you to use your metric units, which is what we're doing. And then we go to the specifications. We set our two chemicals, search for hexane, search for decane, find them. I don't have any other chemicals in this process. Again, in this process, I'm mixing hexane and decane, pumping it up to a pressure, and then putting them in a distillation column. So this first step, we put our chemicals, we find our chemicals, creating the database we want. And then let's go through the tutorial. So you have question 1 in the tutorial. Report the molecular weight of N-hexane contained in the Aspen Plus database. So if you want to find the physical properties, I'm going to click on this, and then I'm going to click on review. Right. Wait for Aspen Plus to, wake up, all this stuff. And if you're reading the tutorial, I highly recommend, read it in detail. It has a lot of interesting tips and things like that. But basically, if I click on review from my specifications tab, it's going to take me all the way down here to another tab, right? It's called the review tab, or the review entry in this tree on the left-hand side. And here you can see all the properties you want, right? API, which is basically your gravity with respect to crude oil. Other parameters, if you click, you can probably find them in the help. And here, molecular weight 86.177. This is your viscosity, freezing point, critical temperature, all types, boiling point, all types of parameters are available in the database. Okay. Question, and scroll down the page a bit, says question 2. Use the find feature to determine how many components are in this data bank. So you click on find, you look at the data bank here, and it's asking you to look at APV 90. So in your case, it will be APV 100, right? Because, or maybe APV 110, because you're using version 11.0, but you're basically looking for the pure 35 database, which is, where is it? Here it is. And you click on it, and then I go to my compounds. You can try and basically find or look up how many chemicals are available in this data bank, right? So once I have my data bank here, I can try and find it from the right-hand side. Let's see. Sorry, so I go to my find. First of all, I add the data bank. And then if you look, follow the instructions here, it's telling you formula C6H14. So I'm going to search C6H14 here, find it. It's going to give me all the chemicals with this string in it. And then I'm going to sort them by data bank and look at, how many components exist in data bank 35, right? So, I mean, these are just basic manipulations for you when dealing with Aspen. And it's good to be able to do these manipulations. And if I look here, yeah, there are no chemicals with C6H14 in the data bank pure 35, okay? And so the takeaway here is get comfortable with these steps, especially how to add chemicals to your database, how to remove chemicals. So if you add, for example, you're trying to add hexane and you end up adding hexanol or whatever it is, just you should be comfortable with how to delete them. Just don't panic. The interface in Aspen can be sticky. Sometimes it's non-responsive. You're doing it remotely. Just be patient. You can always right-click, you can always delete, you can always insert, do all these basic manipulations as you need. All right, so we added the chemicals we want. Next step is always to choose the physical properties, right? So once you get comfortable with this, you always jump from chemicals to physical properties. And in your tutorial, you're being asked to select the base method of PSRK, which is predictive Redlich-Kwong-Suave equation of state. And that's it. So once you select your base method, you're good to go basically from the properties tab, because you defined your chemicals, you defined the thermodynamic relationship between them, and you can take it from there. One thing to note about the specifications is that I have basically two lists I need to go through. First one is common, and it lists all your common property methods. So here, this is where you're going to find your Peng-Robinsons, your SRK, all the cute equations of state, which are very common. However, sometimes if you're dealing with a very fancy chemical like pharmaceuticals, polymers, powers, oil and gas, refinery, water, whatever it is, electrolytes, they have their own set of unique equations of state. So if you don't find it, so if you're dealing with something which is somewhat unique, you don't find it in the common methods, you might want to either try to select a subgroup or select all of them and find your equation of state. And of course, you need to, as you work in industry, as you get more experience, or as you get more exposure to these types of problems, selecting the right equation of state can make a huge difference whether your simulation is accurate or it's a garbage in, garbage out type of scenario, right? So to try to take a mental note of the types of equations of state being used with different types of chemicals, right? So as you can see here, SRK works fine with low molecular weight hydrocarbons. Okay, so once we're happy with this, we can move on to the next step. Something which you might run into is sometimes you might get an error here under parameters. One of the most common things is you might get an error under the binary interaction parameters. You might see like a red exclamation mark next to one of them. If you see that, just open it. It will show you probably a table, and just once you open it, it's gonna resolve, it's gonna extract, Aspen is gonna retrieve this data from the database, right? So don't panic if if after selecting your equation of state or after selecting your components, you have a red exclamation mark, or you have, I think it's sometimes a red circle next to one of these, just open your tree, click on the point where the problem is, and it will resolve itself, right? If you're still having some sort of issue, come to office hours, we're gonna deal with it. Okay. Now once we're happy with this, we're gonna go to the simulation, right? And if you don't want to navigate from using these tabs, you can always, you can always click on the next button. So after putting my chemicals, if I click on next, it will automatically take me to components. If I click on next, it will take me to simulation environment, right? So here I'm gonna tell it, okay, take me to the simulation environment, and it will jump to the simulation tab here. So there are many ways to navigate. Find which way you're comfortable with. They both work fine. Okay, so setting up the flow sheet, there are two things to do in setting up the flow sheet. First thing, setting up your units, and then second thing is setting up your streams, material streams and energy streams. So here I'm looking at part 2 of the tutorial, starts on page 6. So it's telling you first thing you need to do is add a pump, right? And as you can see here, I have all types of units in this model palette here. If for some reason this model palette disappears, you can always click on view here in the top and toggle it to appear or disappear, right? So if you click on this X by mistake, it disappears, don't panic. Just go to view, find it, make it show up again. Okay, so we're being told to drop a pump. So what is a pump really? You won't find it in separators. And all of these are their own separate models. As you get more experience, you're gonna try to get a better feel of which one you're gonna use. Okay, I'm gonna drop a pump here. And again, one thing about Aspen is, or one thing which students usually have a hard time dealing with, is that the controls are somewhat sticky. So as long as I have this plus on screen, it means that you are ready to add a unit. So if I click here, once I add it, I need to click on escape to get back to bring back my normal cursor. If I click here and then click here and click here and click here, you'll find out you're adding infinite number of pumps, right? You always need to escape to get out of this addition mode when building your flow sheet. Okay, let's go back. I'm gonna add a pump. Once I added a pump, usually it's good practice to rename it. So I'm gonna rename it pump 1, right? And once I add a pump and rename it or whatever you want to do, we need to connect the material, the streams going in and the streams leaving, right? And to do this, you see here on the left-hand side of your model palette, you have this thing called material. You click on it and you get this plus sign, right? And when dropping a material stream, you need 2 clicks. The first click could be at the destination, or first click could be at the origin, and then you connect it to one of these arrows, right? And you should always connect it to one of the arrows linking your block you're using, right? A red arrow means a required connection. So if red arrow means that this Aspen will not solve for this pump unless all of these red arrows are connected. A blue arrow is for a special case. So you don't need to connect it, but if you have a unique case, unique operation mode, you will need to connect it, okay? So for our case, we have 2 streams. One stream coming in, S1, and then second stream, I'm gonna click on the arrow and then drop the arrow here, stream 2. Once I'm done, you see that I still have this plus cross here. I need to press the escape button so that I go back to my normal cursor. Let me rename the streams as they have in the tutorial, sorry. I'm gonna rename this stream 1, and then I'm gonna rename this guy stream number 2, okay? And one thing you can do with streams, you can move them, you can, do whatever you want to them. So it helps you, if you like to have your process be very nice and clean, organized, you can do it this way. If you like a very messy process, you can do it this way. It's up to you, but you can always do these manipulations, right? Good. So now it tells you, so once you're done with this, we're gonna specify the flow rate of the stream coming in, right? So in order to do this, let me clean this up here. So I dropped my block, I dropped them, and you should notice that once you drop a unit onto the flow sheet, on the left-hand side tree here, it shows up either under streams or under blocks, right? And a red circle means that you're missing information. So you just have the visual, the image, but you don't have enough information to solve this problem. Whether under streams or under blocks. So in this case, I have missing information in one. So I need to define information in the inlet, and I need to define information for the pump. Outlets, you don't need to specify information, otherwise your problem is going to be over-specified. If you know the answer, then what's the point, right? You just need to specify what's going in and what operation you want to do, and then Aspen will calculate the specifications of the output here. Okay. So let's start by looking at stream number one, which is the input. And we're going to specify the information similar to what has been set in the prompt. So once I click on input here, I get this screen. And as you can see in the screen, I need to specify temperature, pressure. So I need to give it two pieces of information. Temperature, pressure, vapor fraction, I need to give it two out of these three. So if I can give it temperature and vapor fraction, it will be happy. Or I can give it temperature and pressure, or I can give it pressure and vapor fraction. But you need 2 out of 3 pieces of information for Aspen to be able to resolve this problem. Okay, let me go back to the tutorial here, just have a look. So if I go back to my tutorial, we need 100 mole per minute of N-hexane, 100 mole per minute of N-decane, 70 degrees Celsius, and 1 bar. Okay, so let me go back to my Aspen window, and we'll try to set these conditions, right? So I know it's 70 Celsius and 1 bar. So again, I have my units here. I can change it to Celsius. So I'm gonna write 70 Celsius. Oops, do it properly. 70 Celsius, right? And 1 bar. 1 bar, not 70. Here we go. And this is what we have, right? So I set my temperature, I set my pressure. Now I need to set my flow basis. So I need 100 moles per minute of N-hexane, 100 moles per minute of N-decane. So there are two ways to do it. I can set my moles, so I need 100 moles per minute. Where is it? Moles per minute. I need an overall of 200 moles per minute. And I need my mole fraction to be 0.5 and 0.5, right? So this fixes my information, or this satisfies this stream, and as you can see, it turns into a blue check. This is one way to do it. Alternatively, if I don't want to specify an overall flow rate and some fractions, I can just go here directly. So I can delete my overall flow rate. And on the right-hand side, I can just specify a mole flow rate directly. So I can tell it, you know what, it has a mole flow rate of moles per minute of 100 of this component and 100 of this component, right? And this is 200 moles per minute. And this will also satisfy this blue check. So take some time, play around with this interface, see what the different ways you can input this information to meet the specification you need, right? As defined in your prompt or in your base case or whatever it is you're dealing with. Let me do something here. I'm gonna save it because always good practice to save your simulation. And you know, save it in a place where you can find it. And then this is a default thing. So I'm gonna save it here. Tutorial 1, okay, whatever. And let me just save it Give it some time to save, and we'll take it from there. So if you recall from your tutorial on page number 2, it says the pump. So after defining my stream, 100 moles per minute of hexane, 100 moles per minute of decane, they go into a pump where they are pressurized to 5.2 bars, right? So I'm going to navigate back to my main flow sheet. And again, you see these tabs at the top, you can navigate between different tabs you have open. If for some reason your main flow sheet disappears, it happens, right? So if my flow sheet disappears, can't find it at the top, again, you go to your view tab at the top here, click on flow sheet, boom, it's going to show up in a second, and you have your flow sheet ready to go. All right. Okay, so now I want to define the properties for the pump. So I can either navigate to it from the left-hand side. Let me organize this. I always like to have my flow sheet at the absolute left. Anyways, I can either go to my pump from the left-hand side, or I can double-click on the icon, and it will open the pump specifications page, right? Here it is. And as you can see, some of these parameters can be not very familiar to you. You know, if you haven't taken all these pumping cycles in thermodynamics, or you don't recall them, or you're not interested in dealing with them, whatever it is, you just specify one of these four, right? So you either need to specify a discharge pressure, specify a pressure increase, specify a pressure ratio. This is for specific cases, especially gases or whatever it is, or specify the power required to run this pump. And Aspen only needs one piece of information to resolve this pump model. So in our case, you're being told that the discharge pressure is 5.2 bars. So I'm just going to set this here, 5.2 bars, here we go. And this will resolve, or this will basically give you a blue check, means Aspen is happy, it doesn't need any more information. We can move on to the next step, okay? Let's see. So in your tutorial, it's giving you a suggestion to fix a pump efficiency of 0.85 and a driver efficiency of 0.96. And you know, these sort of numbers. So when you're designing a process, pumps, compressors, they're almost never 100% efficient. So you should always try to over design, right? Maybe for pumps, it's always good to maybe set 0.8. For compressors, set somewhere between 0.4 and 0.6. This way you're over designing your plan so that you can always adjust them later while still having a reasonable, feasible design, right? Can always fix an over-designed system, but trying to fix an under-designed system is much harder. Okay, sounds good. So now once you have everything here, you can, let's run the simulation now. So to run it, I can either click on next, and once I click on next, it'll tell me required input complete. If I am missing a piece of information, let's say I didn't specify this, and I click on next, it will tell me discharge pressure must be specified. It will give me the piece of information which is missing. All right. So let's do this, and let's click on next. It's telling me required input complete. You can run the simulation now. Okay, let's run it. And it will show you like a run screen, a control panel for your screen. Processing, and then it will give you some results. Alternatively, if you don't want to click next, or if you're confident everything's fine, you can just click on run directly, and it will run your simulation directly as well. Okay, so it's telling you no errors, or no warnings, no errors. If you have an error, you must resolve it, otherwise your simulation is incorrect. If you have a warning, you can sometimes ignore warnings and use your engineering judgment to move ahead. Okay, once I run a simulation, I can look at my results. And again, to look at my results, I navigate using the tree on the left-hand side. I go to results summary, clicking on this small arrow next to it, boom. And I have run status. It will show me if I have any errors, everything is fine. Calculations were completed normally. You can have a look. If you have any warnings, they're gonna appear here. Streams, this will show you like stream summary, right? When designing a plant, when building a mass balance for a process, you're usually asked to provide a stream summary. This is what will show up here in a second. Okay, here we go. So I have my feed coming in, which is I specified. And then I have my products, my product stream. And you're being asked question 3, report the temperature of stream 2 in Kelvin. Okay, temperature of stream 2, 343.3. Report the total electricity required to operate this pump. Okay, so how do I get the total electricity required to run the pump? You might not find it here, right? Maybe look under models. Might be here, probably not, right? So if you don't find a piece of information in your overall summary, you could look at specific results of specific units under the unit itself, right? So here I have some numbers. I don't have any electricity. Kilowatt, yeah, this could be work. This could work. So I need 0.282 kilowatts. But if for some reason you don't find a result in your summary, I can always go navigate on the tree on the left-hand side here under blocks. I can look at results here for the block, and it will give me the specific results pertaining to this unit. And this becomes very useful when you have a large process diagram where you have too many units and you want to just look at one unit. You can always navigate, and you can see here I have a lot more information. Electricity required is 0.3455 kilowatts. So this is the answer for number 4. Okay. So now let's do the second half of this flow sheet, which is adding the distillation column, right? And if I navigate to my distillation columns, which one would it be? Extreme, it's under columns, right? So under columns, I have all my distillation columns. And as you can see, I have so many models. There I have DSTW, which is Win Underwood distillation column. This is your administer method. RATFRAC is very sort of iterative numerical type of approach designing columns. This block is for liquid extraction. Multi-frac is for complex units where you have internal recycles and side streams and things like that. SC-frac is basically a shortcut version for multi-frac. Petrofrac for oil and gas. And then you have other units. And as you progress through your career, if you become a process engineer, become an expert in a specific area, become a distillation technology expert, whatever it is, you will become more familiar with different numerical aspects of this. In mass transfer, you'll probably cover maybe distillation and RATFRAC, and that's about it. But distillation is a very, very big field. Very big field with a lot of details. Okay. So for this one, you're told in the tutorial you're using the RATFRAC. So let's do this. I'm gonna click on this RATFRAC square here. I'm going to drop it here. And again, remember that controls in Aspen are a bit sticky. So you have this plus, click on an escape to get back your mouse button. And once I do this, let's rename this guy. I'm gonna rename it from B1. I'm gonna call it this. Call as they have here. And then I want to connect the material streams, right? So when connecting a second unit and you want to connect it to an existing material stream, the way to do it is I'm gonna right click on this material stream. I'm gonna reconnect destination. I'm gonna reconnect the destination to the input of this column. Okay, this is how you do it when dealing with existing streams. Right click on the stream, reconnect destination, you reconnect, or if you want to reconnect source, you can do it the other way around as well. Okay, so after connecting the inlet, I have two outlets here. And as you can see, a distillation column has a bunch of outlets, depending on how you want to operate it. For this one, I'm gonna just have a top and a bottoms, okay, from this distillation column. And I'm gonna rename them. So I'm gonna rename the stream 3. And I'm gonna rename the stream right here 4, which is what the tutorial is asking for. Okay, sounds good. Let me save my file here. And this becomes my flow sheet so far. And if I look on the left-hand side here, you can see that 1 and 2 now get a yellow type of, what do you call it? Rhombus, I guess. Whatever it is, diamond maybe, next to them. And this means that, you know, you already have results, but you made changes to the flow sheet. So maybe these results need to be revised. Whereas the distillation column shows up under blocks and I have a red circle next to it. And this means that missing information, right? Aspen wants something from you before running it. So you have to deal with Aspen, right? Okay, so now we're gonna enter the parameters similar to what's shown in the figure you're given, or in the paragraph under figure 111 in the tutorial. So let me navigate to the tutorial to show you where I am at the moment. So in this paragraph here, it gives you all the information. You can read it and try and basically follow the instructions to set up your distillation columns. So let's do this. Let's go back to the distillation column here. And telling you under setup. So I open the distillation column. And a lot of these details, you might not have covered them. It's fine. You're going to get to them by the end of the semester. You'll be familiar with it. So we're telling you set your number of stages to 15. So I'm going to do this here. But as you can see, it's telling you set the number of stages to 15, and Aspen Plus counts condensers and reboilers as stages if they exist. So there are 13 trays in our case. So in our case, we're going to set this to 13. And it's telling you to set, so it's be 13 plus a condensing stage, plus a reboiling stage at the bottom. So I have 15 stages overall. So my number of stages will be 15. My condenser stage, you're told to set it as total. Your reboiler stage will be kettle. You're told to set the reflux molar ratio to 6.1. Okay, so I have here my reflux ratio. It's in moles. I'm going to set it to 6.1. And the boil up molar ratio to 4.3. So the other thing I need to set is the boil up ratio. So be careful, it's the boil up ratio and not the boil up rate. Very different things. So I'm setting my boil up ratio here, molar as well, setting it to 4.3. Okay, so this specifies the configuration tab. They're then being asked in the streams tab, set the feed stage to 7. Okay. So my feed stage is stream number 2, and basically stage 7 means right above stage 6, right? And again, these are distillation, but distillation is probably the most complex unit you're going to deal with in your careers, right? So you're going to get, the more you practice, the more these things become familiar, right? So in stage 7, which means above stage 6. So this is enough for the streams tab. And then you're asked to go in the pressure tab, set the condenser pressure to 5 bars. So condenser pressure here, I'm going to set it to 5. Be careful of your units. I want 5 bar. And leave everything else at their default value. Okay, so I'm doing this and I'm leaving everything else at the default value. And at this point, this red circle next to the distillation column should have disappeared. So you're good to go. So let's run the simulation again. So again, to run the simulation, I go, let's see, home, and I run it. Give it some time, let it run. It will show you the results in a bit. And take your time with Aspen, you know. If it crashes, it's too sticky, it's not responding, it's slow. Very common problems. Just be patient and try to absorb the software. Oh, okay. So yeah, so once I run it, I don't see this busy mark anymore. Results are available. So let me navigate down to the results here. Click on results summary. Calculations were completed normally. Let's check if there was no warnings, nothing, everything is fine. So our simulation ran fine. So you have question 5 and question 6. Question 5, report the total flow rate of N-hexane in the distillate in kilomole per hour. Okay. So again, if you're not familiar with the terminology, distillate is what leaves at the top, condensate is what leaves at the bottom. So if you want to report the flow rate of N-hexane in the distillate, right, I can either look at the, at my streams here, and let's remember what stream number is this. So this will be the distillate stream from my distillation column, so it'll be the top stream. Let's wait for it to load the streams here. It's not responding. Wait, be patient. Hopefully it wakes up soon. Here we go. Okay, so I have stream 1 and 2. So I'm looking for what stream? I'm looking for stream 3. So if it doesn't show up automatically, you can just go back to results summary. And again, I'm navigating through the tabs at the top. Sorry. And here will be stream number 3. And I'm looking at the total flow rate of N-hexane. So let's navigate down. We're looking at the mole flows. And at the top, I have N-hexane flow rate of 5.19 kilomoles per hour. Okay, makes sense, maybe. You just need to start getting a feeling. Let's have a look at kilomoles per minute or moles per minute. Because you put in 100 moles per minute of N-hexane, you expect the separation to be good, right? So I get 86 moles per minute of N-hexane at the top. So distillation is fine, might not be the best distillation out there, but you know, I get most of my N-hexane from the top. Okay. Question number 6, report the total heat duty in the reboiler in gigajoules per hour. Okay. So again, as we said, if you're looking for a specific parameter from one of the units, you need to navigate under blocks to the unit name here and look at the results of this unit, right? So here I'm looking for a distillation column. On the left-hand side, navigating to the results under it. And it's going to show me specific results for the distillation column, which might not show up in the results summary. So heat duty in the reboiler. Let's have a look here. This is the condenser. I have a heat duty for my condenser. It's not what I'm looking for. I have a reboiler. I have a heat duty for my reboiler, and you need it in gigajoules per hour. Okay, let's try to find this guy here. There we go. 1.36 gigajoules per hour. So this is my heat duty for my reboiler. This is the answer for question number 6. Sounds good. Okay, so at the last part, you're being told a little more on your own, part 3, and you're being asked to add a heat exchanger to the outlet of the bottom's product. the end decane product, which cools the temperature of the bottom's product down to 25 degrees Celsius. Okay, let's do this. It should not be hard. This is something I like to do. I just like to close out these tabs because sometimes they start piling up on you. Okay, so I need to add a heat exchanger. You're being told to use the heater model. So what will this be? It'll be an exchanger, right? You're being told to use a heater model to heat the stream here. So let's add this heat exchanger. And again, you're adding units. You have this cross. You need to escape because, you know, Aspen uses a sticky thing. And I'm gonna connect the input and the output of my heater. So again, to connect something to a unit from an existing stream, I need to reconnect destination, drop it here, and then I'm gonna connect an output as well. Okay, and then escape to get out of it. And let's rename our units. Always good practice to rename your blocks, because if you have a process and all the blocks are B1, B2, whatever, I have no idea what's going on when doing specifications and calculations, then you're gonna end up confusing yourself, right? So let's call it heat 1. And I'm gonna rename the stream as well. Oops, here we go. Rename stream to stream number, what's it, 1, 2, 3, 4, 5, yeah, 5. There we go. So you're being told use the heater model, which lets you issue a temperature change without worrying about how exactly that will happen. Okay. However, you'll need to specify a pressure drop. So assume that there is no pressure drop, and then run it. Okay. So I'm gonna double click on this heater to open the heater page. Alternatively, you can navigate to it from the tree on the left-hand side. And again, this tree has everything you need. Okay, so I need my temperature in this exchanger to be 25 Celsius. And this usually refers to my discharge temperature here. And again, you have a bunch of options which you could use. You could always specify temperature change, duty, vapor fraction, degree of superheating, degree of supercooling. And to resolve a heat exchanger, Aspen only needs 2 pieces of information, right? So if you have any of these, plus pressure, of course, or, you know, if I select one from one menu, it's going to disappear from the other menu, right? So if you have temperature, temperature change, duty, vapor fraction, degrees, whatever, or pressure, specify 2. That's enough degrees of freedom to solve this thermodynamic problem, basically. Okay. So in this case, we're being told that to also specify a pressure drop, right? So I need to specify a pressure drop. How do I specify a pressure drop here? So you're being told there are 2 ways to do it. You can either specify the pressure of the heat exchanger to be the same as the inlet pressure. So, or you can specify a pressure drop directly by entering 0 into the pressure field of the heater block parameters input, right? So you can so if I want a 0 pressure drop, the 0 pressure drop means that so 0 pressure drop means, so what's the pressure of this stream? Let's have a look at stream number 4 here. So this stream is at 4.9 atmospheres. Let's change it to bars because this is the language we were speaking a second ago. This was 5 bars. So a 0 pressure drop means that my product enters at 5 bars and exits at 5 bars. So this unit does not result in any change of pressure of the fluid entering it, right? Most units will have a pressure drop, especially reactors, distillation columns. Heat exchangers definitely have a pressure drop, but sometimes when dealing with Aspen, you don't want to deal with this thing, or, you know, if you know in advance that the pressure drop will be very low and you don't want to increase the computational load on your computer, you can set it to 0. And the ways to do it, as written in your tutorial, I can either set my outlet pressure to be the same as my inlet pressure. So I can either set this to 5 bars, or I can set the pressure drop parameter to be 0. Either way will achieve the same thing. So in this case, I'm just going to fix my pressure, my outlet pressure, to be the same as my inlet pressure, to be 5 bars, and I'm going to run the simulation, and this should conclude part 3 for this case. So let's run it, and let's answer questions 7 and 8 from this tutorial. Okay, it's is it not happy with something? So let's go next, see if it needs anything from me. Required inputs complete. Okay, so let's run it. Okay, so try and find no errors, nothing. Okay, good. And question 7 is asking you report the heat duty required to do this in gigajoules per hour. Okay, so let's go to our heater block and let's look at the results here. And heat duty in gigajoules per hour minus 0.47 gigajoules per hour to deal with this or to do this cooling to 25 Celsius. And a negative number represents cooling, right? So it's telling you that a negative number, this means that this heat exchanger is performing a cooling operation. And then question number 8, report the mole fraction of hexane in the distillate if you feed the mixture to the column above stage 3 instead of stage 7. Okay, so question number 8 deals with this process, and you're being told that to report the fraction of N-hexane, in the distillate, which is at the top, if I feed the mixture above stage 3 instead of stage 7. Okay. So if you remember in our original simulation, I was, so I double click on the distillation column, I go to my streams, and this is where I specify where my feed stream is entering. And in this case, you're being told to set it to above stage 3 instead of above stage 6, which is stage 7. So I'm going to change it to above stage 3, and I'm going to run it to see what the mole fraction of hexane is in the distillate. Okay, sorry, simulation is complete. So we're looking at the stream number 3. Again, I have 2 ways to find this result. I can either look at my streams under results summary on the left-hand side directly. So if you're following my mouse, I can open my stream 3 under streams and look at results directly, or I can just double click on this guy right here on my flow sheet and it will open stream number 3 results directly, right? Okay. So what are we looking for? Mole fraction of hexane in the distillate. So you go down, mole fraction. Hexane has a mole fraction of 0.9988. Oh, look, you see, if I change if I change where I feed this, I get a much better separation here, right? So I check. Remember last time it was 86, still 86. So I mean, separation doesn't change much, it seems. But the mole fraction is much higher. So for question number 8, the answer is 0.998. Okay, this is the end of tutorial 1. I'm gonna spend a few extra minutes just going over homework 1. So I'm gonna save this as tutorial 1. And then I'm gonna resave the file as homework 1, numbers 1 and 2. just to go over them quickly. All right, so let me save as well. So I'm going to use the same file. Save it as a compound file. So tutorial 1, I'm going to also save it as homework 1 and 2, because if we navigate to your homework, okay, sorry. Let's go to the PDF here. Okay, homework 1. You have first 2 problems are Aspen problems. So problem number 1, repeat tutorial 1 and answer questions number 1 to 8 for cyclohexane and N-undecane instead of N-hexane and N-decane. And you're being asked to run the separation at 8 bars instead of 5 bars. Okay, let's do this. Let's change it all. So you're using the same process, but I'm just changing some parameters. Since my flow sheet is the same, I'll just use the same file. Let me just navigate to Aspen here. I'm using the same file right here. And I'm gonna navigate back to my properties tab. So to navigate to the properties tab, on the bottom left-hand side, you can just click on properties and let's clean out this, close out this tree. And I'm going to basically my components, specifications, and instead of hexane and decane, I need to specify cyclohexane and undecane. So let's find cyclohexane. Cyclohexane. There we go. So I want cyclohexane, so I'm gonna add it. And then I also need N-undecane. So let's search for this guy as well. Try to get him into our simulation. Okay, it seems to be clunky for some reason. Let's just do it properly. I'll close it and open it again. N-undecane, let's search. There we go. This is the guy. It's Adam. Do you want to replace? No, I just want to add it. So just be careful. Usually I need to just click on a new space and then add it. But in this case, just be careful of these. And I'm gonna get rid of these two. So I'm gonna get rid of N-hexane and N-decane because we're gonna use the 2 new compounds. So let's delete these guys. Yes, delete them. We're fine. And you see, once I deleted them here under methods, this is what I was talking about last time. Parameters, pure components. You're gonna get a bunch of errors, whatever they are. So how do we resolve these issues, right? Let's click on next. Component IDs must be specified. So it seems that a computer or Aspen is not happy with something here. Okay, let's have a look here. Let's see. Click on this next. So because we already had the database, so that's one of the flow issues or workflow issues with Aspen. It can get a little clunky when modifying files. I think a way around it is at the top here, if I click on just retrieve parameters, it should resolve it, where I'm just telling Aspen, just go get this information from the database and fill out, just do what you need to do. Stop complaining, right? So give it some time. View parameter results. Results are on the parameter. I don't want to view them. It's fine as long as you have them. We're good. And so now Aspen retrieved the results. So if you're, so you might get this error, you might not get this error, but Aspen tends to be clunky in these strange ways, right? So you can always retrieve the information of their known chemicals. If they're very unique chemicals, you can always try to extract them from other databases, many different ways to do it. But just don't panic, deal with it, and you should get there. Okay, so we're done with our properties. Let's go to next. And you can run property analysis setup or go to simulation environment. Let's go to the simulation environment and start modifying our process to do the type of thing. So the second thing is we're using cyclohexane and undecane instead of hexane and decane. Second thing, we want to run our separation at 5 bars instead of at 8 bars, sorry, instead of at 5 bars. So once we go to our flow sheet here, you see that stream number 1. Okay, let me close out of these tabs. I don't like having them open here. Okay, let's go to stream 1. So I look at my tree. Stream 1, I have an Aspen needs some information to be able to resolve this problem. And let's see. So the thing is, once we deleted our initial components, our flow rates disappeared. So I'm just gonna reset my flow rates to 100 moles per minute and 100 moles per minute here as well. Stream 1 is happy. Okay, good to go. And then the next thing we're gonna change is we're gonna change our pump from, we said what, from 5 bars to 8 bars, right? So I'm gonna change my discharge pressure on the pump to 8 bars. And then I'm also going to have a look at my distillation column here and see if I need to change anything. So my pressure here. So I'm gonna run my pressure as well at 8 bars. So I'm gonna change my pressure at 2 locations that I run this process at 8 bars instead of at 5 bars, okay? So once we make these changes, you see on the left-hand side here, it's telling you input changed. It's fine, so let's run the simulation. So I'm gonna run it from here. And once you do this, you should be able to see all of your results. And then you can answer questions 1 to 8, which is looking at this heat duty, looking at this composition, this and that, this temperature, all of this stuff. You can always extract them from the results. Okay. And I see my streams, all this stuff. And then number 2, you're being asked to make one change that would increase the undecane mole fraction from distillation column bottoms to greater than 95%. Oops. So I'm gonna leave number 2 to you. What I suggest you do is you can further increase the pressure. You could maybe change your feed rate, play around with these parameters, see what condition you're gonna reach that will give you indicate mole fraction in the bottom is greater than 95%. So the bottom stream, if you recall, is stream number 4. And at these conditions, what's the mole fraction here? The mole fraction from the bottoms of undecane is 0.8. Okay, so you could increase the pressure. You could, if you want, let's try something. Maybe I'll feed it at a much higher stage, you know, see if this makes sense. It might backfire, who knows. But, you know, experiment with this since you haven't really covered this in mass transfer. Experiment, try to see what happens when you increase this, maybe increase your reboiler ratio, etc., and see how could you increase your bottoms composition to greater than 95%, okay? So let's run this. I'm gonna try a couple of things. Increase the feed stage to above 10. Let's see if this makes any change, makes it better or worse. Let's have a look. Okay, let's look at my results summary here. Okay, so changing the feed stage doesn't have an effect, right? Still 0.8. Okay, so if it doesn't have an effect, let's just bring it back to 7. Um, let's see. What if I increase my number of stages here? What if I make it 20, for example? Will this make a difference? Let's try it and run it and see. Yeah, it's taking some time to run. It's fine. Just be patient. Hopefully on the university servers, it runs much faster. I'm running this on my laptop. Um, am I missing something? Okay. Okay, increasing the number of stages, does it have any effect? Oh, okay. Maybe last time I wasn't even patient on the results because I thought they would run much faster. But just wait until you get the final confirmation that everything ran completely. Input changed here should be changed to results available. Look at your results, all this stuff. So I'm gonna end this video here because it's starting to drag on. But yeah, play around with it and see if you can achieve bottoms composition of n on decane greater than 95%. All right, thank you very much. I'll be posting the tutorials. If you're having a hard time with any of these tutorials, please come to office hours. It's very important that you become familiar with Aspen. All right, thank you.